Okay, let's begin. We discussed last time the word identity for conformal field theories, and I remind you the form in which we wrote it. It refers to the energy momentum tensor, which we alternatively called either T when in Euclidean region, or not necessarily, or T++. Sometimes it's convenient to have these light cone indices. They indicate that it is spin 2. Each plus is a vector index, and it's just the that's just notational comment. And with any operators, any primary operators, the equation which we dealt with was this one. So when you know the correlation functions of certain primaries with the energy momentum tensor is expressed in terms of the correlation function of the primaries, and we explained that this is actually because we have because the energy momentum tensor is traceless. Then we have enough equations following from that means that we have large symmetry, which is sufficient to determine its correlation function. And using this identity, we actually realize that there are many secondary or descendant operators which must be present. Namely, we looked at the fusion of this energy momentum tensor with some operator at z as z goes to 0. And what we found was that as z goes to 0, it has the expansion. First of all, there is a term 1 over z square coming from here that gives us delta divided by z square phi of 0. Plus, there are terms. We find the term 1 over z, and here we have d phi dx x equals 0. Plus, we have a term which we denoted z to the 0. I'm just repeating we denote that this term, excuse me, like that. I shall explain the origin of this notation in a moment. And in principle, what's important, since we just observe that there is this there are these regular terms here, and their presence indicate that if we have some primary fields with dimension delta, there will be infinite number of secondaries with dimension delta plus some integer. Since the whole energy momentum tensor is determined from here, that means that we know how to calculate this object. This object, so far, it is just a notation. We simply denoted this operator, and as you can guess, we will actually obtain terms like z to the n here with which will be L minus 2 minus n. What we can actually present it. So these are the descendants. Important thing also have to remind you from yesterday that L minus 2 phi of z, its correlation functions are known. They're just the same type of differential operator applied to the correlation function of the primaries. So we have sum of delta k z minus xk square plus 1 over z minus xk d dxk applied to phi of z, phi of xn. What is important here is that while we know this term, this descendant, we know means that we know how to calculate it if we want to. It is not locally expressed in terms of f of z. For instance, L minus 1 phi, we noticed that it's by definition is dz phi. And so it is expressible in terms of phi. One might think this should be something like second derivative, but no way. The second derivative is L minus 1 square, and it's different in general from L minus 2. So we have a totally novel new set of operators here, and they must be present because when we are building the theory, we must check fusions of all possible operators with each other. Okay, and now we will see how to. First of all, let us define its again convenient notation to write down the Laurent expansion of the operator T of C. If you look at this formula, which we derived from the word identity, it is just in principle it's ln z to the minus n. And for primary operators, that's one of the definitions of primary operators. The term, for example, L1 would enter with the coefficient. So if you have, for example, L1, it will enter with the coefficients z minus 3 and so on. So when you collide it with the operator phi, we see that there's no such term, which symbolically we write down as a condition L1 phi, or basically Ln phi 0 for all n greater than 0. L naught phi is delta phi. If the operator is not primary, then we indeed will get what would be the simplest example of the non-primary operator?
L minus 1.
What? Setting it?
L minus 5, L minus 1.
Yeah, if we simply take we actually looked at this example already. if you take derivative, simple derivative for L minus 1, which is the same, then it's clear from here you get the term 1 over z cube, which corresponds to L1. So we conclude that if you have L1, L minus 1, phi, what it will be equal to if you just look at this line, and you will immediately can read it from this line. I remind you that L minus 1 was a derivative, while L plus 1 is the coefficient in front of z minus 3. So what would be this expression? What? Yeah, it will be clearly 2 delta multiplied by phi, or it will be 2L0 phi. So how I got this? I just noticed that when I differentiate, slightly clumsy since I put 0 as an argument, but let's differentiate with respect to this 0. Consider this as a letter O, and then take the derivative with respect to DDO. Then the only thing which in the whole expansion, which will give you 1 over z to the cube, will be clearly differentiation of this term. As a result, we have this, and since it's a primary, you can actually conclude that the commutator of these operations is given by this formula. Now, when I'm talking about commutators and these operations, let's ask ourselves the question, commutators in what space? What does it mean that we are dealing with a purely classical theory? So it is not entirely clear at the moment what do we mean by the commutator. But in fact, you can view this in several ways, and we will be discussing today these several points of view. The most conservative point of view would be simply to say, let's keep these definitions, but let's analytically continue it to Minkowski space. Then we have operators, and they are operators in the usual sense in the Hilbert space. I shall explain this in a moment, but there's also, before explaining, I shall describe another point of view. You can keep things Euclidean. So these are not phis are not operators. There's just some fluctuating variables. But we have operation in the space of all correlation functions. That's an important concept and worth remembering. Although in this case it will give us the same thing as traditional Minkowskian view. So what I mean by that is that we discussed last time that if you introduce the operator T epsilon, the object T epsilon, which is integral over some contour C of T of Z epsilon of C, then when you insert T epsilon into the correlation function, it actually performs infinitesimal transformation. Sum over k. This is infinitesimal conformal transformation. So you can really view this as you can imagine the space of all possible correlation functions, like it's a little bit like going to the second quantization in quantum mechanics. And then this operator acts in this precisely in this space. That's another possible view, and we can actually look now at the commutators. We can look at the T epsilon 1, T epsilon 2, and so on, and then permute it. Or I can put it in an even simpler way. It's a kind of interesting thing, these Euclidean operators. So the simpler way is to say we perform fusions of T of z with some operator. Suppose we have 2 T of z. Of course, we will write the word identity for them just as well. I will do this. But how would you define if you just have this function? Forget for one moment about this operation. But just in a very simple word, how can we get the commutator by fusions, by operator products?
Commutator or the correlation function.
What I mean is that you can fuse first z2 with x1. So you have the point x1, you take z2, and you fuse them. And then after that, you fuse the result with z1. And then you can do it in the other way around, in the other order. And the result, generally speaking, will be different. So you get the possibility to introduce operators in the non-commuting, in the correlation functions, which by themselves, the variable field by itself is just the classical variable. And I shall, for completeness, I will tell you about Minkowskian version of this argument, and then we will proceed with derivation of anomalous dimensions. The reason why all this is interesting is that it is by subtle algebraic procedures like self-consistency and operator product expansion and so on, associativity, you are able at the end determine theoretically possible and the set of possible anomalous dimensions and the structure constants. In some cases, not always. And that's so you are not solving field theory conventionally, but in some algebraic way. Okay, in Minkowski, I assume there is some general comment which I will not, which you must be familiar with. I shall very briefly indicate what it is. So let's take the, for example, in 4 dimensions, the correlation function of free field, the T product. Then it is a function of x squared minus I0. Why it is the function of this type? I don't have much time to explain this, but it's actually simple. If you look, it's the origin of these I0s is this. Again, that's the stuff you find in textbooks on QFT. You have phi 0 n square e to the minus int, I assume is 0. And you see that this is, in order to make, if I continue to imaginary time less than 0, the sum becomes better and better convergent. So in the whole lower half plane, I don't have singularity. The function of time is analytic. And if you remember the definition of this thing, that you have t product, which means that for t greater than 0 it is this order, for t less than 0 it's the other order. I'm going intentionally very quickly because I assume you know this. Important thing is that when x square, that this function in the complex plane of x square, and x square is t square minus x square, is the following. It's the analytic function with a cut or a pole, generally speaking a cut, for x square, let's call it s, for s greater than 0. And it's analytic here. What we mean by Euclidean field theory are the values which lies here. For example, you can look at the correlation function at the coinciding time. It will be a symmetric function of x1 and x2. And clearly, if you permute it, I'm talking now not about our construction, but about just full-fledged field theory, in which this is operators and so on. However, this thing commute because the cut, there's no cut here, and to get it from in one order, you analytically continue here, in the other order you analytically continue here. So the commutator of two things in field theory is f of s plus I0 minus I0 minus f of s plus I0. And since the commutator must be odd with respect to time, it also contains sine of x0. So it is the way you from the complex Euclidean point of view, complexified Euclidean point of view, different order of operators correspond to different approaches to the cut in the complex plane of S. And in this way, you have a complete algebra of operators and so on. And if you calculate, for example, this in Minkowskian way, it's perfectly possible to do. The only thing you have to change here as you go to Minkowski is this. It's that you have all, instead of 1 over z, you substitute 1 over x plus I epsilon sine x minus. Now where it comes from, minus actually, where it comes from, it comes from the fact that you have to have this thing, and if you now this is, by the way, well, about this stuff. It actually, if you are not completely knowledgeable about that, I really recommend you to ask me more questions after the class, because it's important thing, which would be worth the whole lecture. But I just since it's, and I would also say that it's not very clearly it is discussed in the standard textbooks, but not very well. So it would be. I really recommend you to talk to me after the class about this. Okay. Before we leave this thing, it's an interesting point is that 1 over z is a fermion propagator. And it's Minkowskian version also. That is massless Dirac equation. Indeed, the massless Dirac operator is D minus for left fermion, and it gives you the delta function that we discussed. Well, the reason I'm returning to this is that it is by looking at this formula you can see the spin statistics theorem. So how would you extract the spin statistics theorem from the formulas which I wrote down here?
You could just substitute z2 minus z here.
Yeah, we have psi of z1, psi of z2 is 1 over z minus 1 minus z2. That would be better. So continue. How do you see the spin statistics theory?
You could take psi of z2, psi of z1, and add them up, and they add up to 0. So.
And so,
if we exchange z2 with z1,
yes,
we get the minus sign.
Yes,
so.
Yes, right. The spin statistic appears this way. We have the Dirac green function, which is this, which automatically is just by the properties of Dirac operator is anti-symmetric with respect to z1 and z2. Since it's anti-symmetric, it cannot be identified with commuting variables here. So what I'm saying is that let's go to the space, to the Euclidean region, or more generally to the space-like region. In space-like region, things commute. For example, this bosonic thing is symmetric function of x1 and x2, and the Klein-Gordon operator has the property that its green function is indeed symmetric. So you can identify it with this average. Dirac green function is anti-symmetric, so it would be a contradiction to assume that psi are commuting, that they have Bose statistics. Dirac operator enforces Fermi statistics, and that's kind of interesting. That's the spin statistic theory. Okay, that was a digression. Now let's proceed here, now that we understand what the commutators mean. And we have this simplest example. But we still need one small ingredient to complete our job, which is the property, some certain property of energy momentum tensor. Namely, one might think, let's assume for one moment that energy momentum tensor is a primary operator. We don't know a priori what it is. All we know from the word identity for T is that it has dimension 2. Scaling is such that that it has dimension 2. Now let's assume that for one moment that it is a primary operator. It is a primary. If it is a primary operator, then we can actually write down the word identity. Its transformation. Excuse me. Then its transformation when you transform coordinates will be epsilon of z dzt. That's the usual stuff with the primary operator. Now, since we see that it has dimension 2, we have 2 dz epsilon multiplied by t, and that's it if it is a primary. And t epsilon t of z should be equal, according to this formula, according to our assumption that it is a primary, it will be epsilon and this thing is clearly 0 because expectation value, you don't really have any, because things are translational invariant, so 1-point functions are on a plane or on a sphere are 0. There are cases when they are non-zero, like with high topologies, but that's not what interests us now. So we conclude that in this case, would be 0. Now, that is strange, and that actually contradicts to a very general theorem, which I will tell you now. Again, I shall return for one moment to the standard QFT. And this, well, there is the, let's take the standard case to fully appreciate what it means. Let's take the standard case of QED. And in QED, we have operators, we have current, gamma 0, and its spatial component. And if you calculate the naive commutators without using operator product expansion, you just calculate the commutators. Then you will get the result that it is simply 0. They commute with each other. Now, actually, Schwinger noticed that this commutation relation, which is analogous to this fact, contradicts the first principles. And his proof is very simple, and I will reproduce it. Such commutators can never be 0. Let's use the relation, the continuity equation for the current. And let's take the vacuum expectation value of the J0 dot. This vacuum expectation value is then we put intermediate states here, and you will have we can always write here the commutator of H and 0 minus vice versa. And when you saturate things with full set of states, it all reduces to J0, H, J0. I assume that vacuum energy is 0. That's just a convention. And you have and that is always positive when the vacuum is stable. So positivity of norms implies that it is non-zero here, and it also implies, in this, more or less in the same way, that it cannot be zero here. So we need, we conclude that the energy momentum tensor, the basic object, is in fact a descendant operator. And again, let's determine what kind of that means that this formula cannot be right if I need all norms positive. The right formula is, we have the same thing. Plus, I must have, since t scales like 1 over z square, I can add, in principle, the term, and epsilon scales as z, some constant c divided by 12, that's a convention. Nothing fundamental here, just convenient normalization, multiplied by dz to the cube of epsilon. Now, why dz to the cube? Because we have epsilon scales as z, so we have on the right hand side scaling, it scales like t, like z minus 2. So this also scales normally, this scales like 1 over z square. And now you can compare this with the formula for the primary operator phi prime of z, which we derived at some point. It's epsilon dz phi prime plus prime means differentiated, plus we derived delta plus 1 dz epsilon phi prime. So far so good. It's just the standard primary transformation law for the field delta with dimension delta plus 1. But we notice that there is also the term delta multiplied by dz square epsilon multiplied by phi. So it's the descendant operator is expressed, its transformation law is expressed in terms, not only in terms of itself, but also in terms of this primary operator. And this indeed is, it has all correct dimension, because dz square epsilon scales like 1 over z, and that's the same as scaling for phi prime. And now I'm ready to ask you the question by observing this formula. So we said the energy momentum tensor is a descendant. Descendant of what? What is the primary operator?
Identity.
It clearly should be identity, because we have nothing here. What is it? It's multiplied by, it's not an operator. And from this we immediately derive, and from the word identity, And that implies that the correlation function of t of z, t of u, will be c divided by 2, c minus u to the 4th. Okay, I'm going relatively quickly here. I hope it's okay because this stuff is it's written in many textbooks, and it's actually hard to spoil it. You cannot write too bad about it. It's simple, straightforward. So if you are not familiar with it, read some book on CFT. But now I'm actually turning to the way to use it and how to identify it with the models. So how can we decide which? We will now classify some CFT and discuss the question what they describe. In a sense, it's a formalism which is looking for the system to describe. There's some classical Italian play entitled 6 Characters in Search of the Author. And here there will be several theoretical constructs looking for the system to describe. Anyway,
The partial derivative is that cubed or squared?
Excuse me? Which one?
Rather the m.
This?
To your right. Delta partial square.
Here?
Yeah, is it cubed or squared?
It's square.
It's squared. So how do you, I guess, how do you compare it to this expression where it's cubed? So we compare it to this expression here.
Oh, yes. The difference is that we have, in both cases, we have some higher derivatives of epsilon. Here it's cube, third derivative. Here it's second derivative. And it is multiplied by the primary primary operator, which gave rise to this descendant. Now, the difference is actually, it's an interesting question. The difference is, let's discuss why it is dz cube and it's only dz square here. The phi prime operator, we can write it down as L minus 1 phi. It's L minus 1, I remind, it's just a derivative. So it is actually descendant of on the level 1. Its dimension is delta plus 1, which is on which level is t is a descendant of the unit operator, because this expression is not multiplied by anything. It's multiplied by unity, so to say. At which level we have a descendant operator of which level? So what would be, I'll ask it more clearly. We have this relation. What is the t of z?
All of those.
Huh?
All of those.
L?
All of the levels.
All?
Yeah, every one of them, because it's a lower Roman expansion.
Oh, no. Look, that's important to clarify. Okay, I think I can erase this. You see, when L minus 1 is a raising operator, so the dimension its dimension is dimension of phi plus 1. It increases dimension by 1, which is trivial statement because it's just a derivative of phi. Now, what I'm asking you is that all descendants have the form of sum of these guys applied to the primary operator. And I'm asking you about T of z. And what you said is that T of z, we have the Laurent expansion of T of z. We have some operators Ln. Now we want to actually write down T of z as L something applied to the unit operator. If you see, unit operator has dimension 0, T of z has dimension 2. So the only relation of this type you can write of this type is that T is L minus 2 applied to the unit operator. Of course, there are also higher, that's at when we take it at z equals 0. As you go to other places, then your answer is correct, and indeed you have all higher L minus n. But the analog of this formula is just this one. It's degeneracy at dimension 2. Okay, let's get going. I'm digressing too much. By using this formula, you can. This formula is important, and you can derive the relation for T epsilon 1, T epsilon 2, the commutator. And without C, it will be just the algebra of conformal deformations. So it will be T again, I will go quickly here. It's simply how you derive this. You simply take, say, epsilon 1 here. You literally take the commutator. I would say the T and then calculate. It's non-commutativity here, in spite of the fact that everything, it just came to my mind, the analogy is how to explain that we have non-commutative algebra, although we're dealing with a purely classical system like the Ising model. The explanation is that it's the commutators of the various symmetry. It's just that, just like this eraser is purely classical, however, if you rotate it 90 degrees this way, 90 degrees this way, and then it will not commute with the opposite order. So in the same sense, you have non-commutativity of these classical things, and it translates also, as I said, you can also treat it quantum mechanically. Or you can, probably the closest to this classical treatment is that what I said, that it's operation in the space of correlation functions. But there is also this C divided by 12 term, and it gives something important, namely when we go to the Ln operator, we get the so-called Virasoro algebra from here. This first part, I shall write it down and then we will. This first part is purely geometrical. Namely, it's just the changes of variable which don't compute. So you imagine that you change variables by epsilon 1, then by epsilon 2. It's literally rotating the eraser. Nothing more than that. This thing is more tricky. Actually, mathematicians discover, although it's called the Virasoro algebra, it's somewhat anachronistic because several years before Virasoro, Gelfand and Fuchs, and here we have actually delta n plus m0, derived this algebra from the purely mathematical consideration, and try to think how they, of course, nothing was known or thought by anyone about conformal field theory or things like that. That's totally different story. They were just interested in algebraic properties of changes of variables, purely mathematical question. And how do you think they could derive this extra term in the algebra? What kind of question they were asking? Just what I'm asking is that just give me a purely mathematical reason why this is a possible algebra. Yes, but why? It's not an arbitrary central expansion. It's only this. If you put, for example, n cube here, it would be a disaster. But with this thing, it's not a disaster. It's consistent. So that's basically the question. Why it's indeed this term is called the central extension. All right. Gelfand and Fuchs derived it, and it's unique. That's what I'm saying. It's unique. If you try something else, it will not work. Why? What will fail? Jacobi identity, yes. They simply analyzed a very well-defined and well-posed mathematical question, which central extensions of the algebra of diffeomorph, these are algebras of one-dimensional diffeomorphisms, what would be the central extension consistent with the Jacobi identity? And that's the answer. And here it appears in our context, it's not a possibility because the algebra, of course, is consistent. Mathematically, the algebra is consistent without central extension. Nothing wrong with it. And by the way, when I was playing with the eraser, which part of this algebra I was testing? Yeah, but there is a rotation group actually without central extension, which is a subgroup of this thing. Okay, so in our case, central extension is a must if we want to have a unitary theory, a theory with positive energy for which the Hamiltonian is bounded. It's not that it is always the case. There are some theories, we will be talking about them a little, which are non-unitary and therefore nevertheless physically meaningful. These are theories, conformal field theories, describing polymers on a surface. and they don't have clear Minkowskian interpretation. If you do Minkowskian, you will find some negative norms, and it's not entirely clear how to interpret this. One of the guesses is that it might describe some unstable, metastable vacuum, but that's not completely certain. But in any case, it's not that we commit some great sin by disregarding central extension. It's possible, but this Schwinger argument tells you that its central extension is related to unitarity. Now it's very few things which remains to be shown about conformal field theory. Namely, let's look at the primary operators. Suppose we have some primary operator, phi. And we know now that we can also calculate L minus 2. So we have this possibility. Now, if we take, let's return for one moment to the Ising model. And in the Ising model, we expect that it should be somehow related to the phi-4 theory. So the Ising model, we actually discussed, we start with the interaction lambda phi to the 4th. And so the equation of motion is lambda phi to the cube. And somehow it should be related, and phi corresponds to sigma, it's just the spin operator. And with spin operators, we can form the product of three spins. It will be proportional. We will see how to consider these fusion rules. And generally speaking, it will be proportional to sigma because of when we collide three operators, the dominant operator is sigma. Plus, it's possible to have the terms like L minus 1, L minus 1 sigma. That will give us the Laplacian. So far, so good. But we also will have the operators of the type they, generally speaking, will appear in the expansion. So the question is, and there are operators L minus 1 square phi which can be added. So there are many possible terms which we expect to appear. How to reproduce this thing? Probably I should have. Okay, I think I'll manage. The point I'm trying to make is that in order to reproduce the equations of motion, there should be something special to conformal field theory. Namely, it should the spin operator, the operator L minus 2 and L minus 1 square should be linearly dependent. If this is so, if they are linearly dependent, then we will actually obtain some resemblance of the equations of motion. And we notice we obtained it. Actually, let me give you a slightly more general picture of what we're discussing. In quantum, suppose, let's return once again to quantum electrodynamics. In quantum electrodynamics, we have the equations of motion but we know that those operators are singular, so there are divergences. So in fact, it should be understood in the following way, that when you take this operator product expansion, then most singular term, as epsilon goes to 0, will be epsilon to some power multiplied by d mu f mu nu. That's what this equation of motion is. That you take the renormalized theory which describes from which ultraviolet scales disappear, and the general prescription which arises from this is that you always read the equations of motions the other way around, from the right to the left, like Hebrew alphabet, Hebrew writing. And you should perceive those equations of motion as operator product expansion. They are not, the equations of motion by themselves do not exist. They are just the consequence of the operator product expansion. And it's a little bit vague now, because maybe I should have made some more explanations before, but I will do it now, and you will see that it is quite good and reasonable concept, that operator product expansions, they help you to identify which model you have conformal field theory with certain operator product expansion, and these OPE define which model you are describing, which is not trivial thing, because when you derive this operator product expansions, conformal field theory, it's not always clear what they refer to. And not, actually, it's, I can tell you that when it was quite a surprise that there is some algebraically defined theory which could be identified with the Ising model. You see, the point is that we will determine, for example, the spectrum of anomalous dimensions, and this spectrum, it's not a priori clear that it will coincide with anything, but for some models it coincides with the Ising anomalous dimensions, and that's not far from obvious. But let me make it more clear, because it's an important point. And so the first question which we ask is, let's suppose that we have an operator of the type let's call it chi. So it's if the dimension of chi is shifted by 2 from dimension phi. This operator, first of all, we can ask whether chi by itself is a primary or not. Generally speaking, it is not. Generally speaking, it is a descendant operator, almost by definition. But what we have to check to see that if it is simultaneous, if we started with some primary operator, it can happen by some accident, in a sense, that certain descendants are simultaneously primary operators. So what shall we check here?
Act by L1.
The what?
Act on chi by L1.
That's it.
On chi by L1.
Yeah. We first indeed look at this thing, and we get some here we have these conditions first.
Sorry, acting always means taking the commutator, right?
No. Let me explain. Thank you for this question.
Because L1 annihilates phi, right?
Yes.
Okay.
Yes. Yeah. Good. No, that's very good. It's a little bit tricky, so it is very helpful for me when you ask these questions. Otherwise, I'm not sure whether I'm explaining clearly or not. Okay, so indeed here, since L1 annihilates phi, we have this condition, and it tells you that if you can easily calculate this, and again this is something which is done in many books, that if you take this operator, this linear combination, for any delta, then this term is annihilated by L1. Generally speaking, it's not annihilated by L2. I shall explain what it means. But I hope the thing I hope is clear is how you calculate and what we are doing. We are really, this is some well-defined operator with well-defined correlation functions. We know all of them in terms of correlation functions of phi. This is simply a second derivative of phi. This is, as I discussed at the beginning, something else. And now we have this Virasoro algebra. It contains a subalgebra of three variables. It's just we derive this, and this is the algebra of which contains three generators. It's the algebra of SL2R, and if you complexify it, which, by the way, well, if we have a complex plane, all these operations, they correspond to some transformations. Which three transformations are described by this subalgebra of the Virasoro? Huh? Yeah, but what kind of epsilon? It corresponds to three possible changes of variables, epsilon of z, which are what?
Constant.
Yes. There are three transformations which we discussed last time. And these are just the infinitesimal version of the Möbius transformation. Is just infinitesimal version of this, and these three transformations are precisely what we're talking about. Generally, if we call the classical without C term generators of these diffeomorphisms, generally it's z to the n ddz plus let me check if I'm correct. Yes. You have this, here is Zn plus 1. If you take the commutator lambda n lambda m, I suggest you as an exercise to get n minus m lambda n plus m. And the subgroup corresponds to n equal plus minus 1 and 0. These are precisely these generators. And they correspond to the Möbius transformation. From the point of view of the vacuum, what is this? What is the special role of these generators? How they are different from the others?
The vacuum is invariant.
That's right. All others generate Gallstone boson when they act on the vacuum, as we discussed, while these ones leave the vacuum unchanged. Yes.
It's like confused with the definition of vacuum here. So
Okay.
basically, it seems that it's now a definition of vacuum as something which is or not.
Okay, let me try. Vacuum here is just a unit, corresponds to the unit operator. There are correspondence between states, and your confusion is well justified, because I'm talking about several formalisms at once. In one formalism, we have Minkowski space. We have the vacuum and operators acting on the vacuum. In the formalism we are discussing here, we consider basically our basic objects are correlation functions. We don't introduce the vacuum because we are in purely classical region. And when you have, and we have a primary operator which corresponds to the states. If we go back to Minkowski, they would correspond to the different states of the system. Now, the important thing is generally we have descendants L minus 1 phi, and we have L1 phi is 0. And L0 phi is delta phi. And once again, you can perceive it, L minus 1 phi is just a derivative of phi. You can understand this as inserted in correlation function. So you can, one point of view is that let's forget about the states, vacuum, and so on. We just have the set of correlation functions, and these are something which you insert into correlation functions. Now, when we have a unit operator, the unit operator we have, this is the special case of it, is that it's indeed 0. It's unchanged by this descendants of, there are no no projective descendant, L minus 1 descendant of unit operator, for the simple reason why it is for example, for the unit operator is 0. Remember what is L minus 1, how it acts. Derivative, and the unit operator doesn't depend on anything. So this is a consistent point of view when we talk about the correlation functions only. You can actually avoid, if you want to, it's not rational, but it's possible to avoid altogether mentioning of states, Hilbert space, and so on, and deal with only with correlation functions. This commutator is just a geometrical operation on the correlation functions. Then you can also go to quantum theory and introduce creation annihilation operators and define L in terms of these operators. That's also possible. And then there will be the correspondence between primary operators and the states. And the unit operator will correspond to the vacuum. Okay, what I was saying, that we have no Goldstone bosons because all three things are 0. Ln applied to the unit operator is 0 for n. And that is equivalent to saying that correlation functions are invariant under Möbius transformation and only under Möbius transformation. So you see, it's a little bit tricky, and it requires some adjustment to understand these things. And to understand these things, you cannot really, although I said that it's quite possible to forget about the states and work with correlation functions only. It's not really the most convenient way. You have to use all languages at once. Basically, that's the most reasonable thing. And by the way, we started it L minus 2 applied to unit operator. It's not a 0 anymore, and that's the Goldstone field. L minus 2I, it's T of Z. And all other descendants, you can take the descendants of the unit operator, and they all will correspond to various Goldstone bosons, combination of Goldstone bosons. So that's how things stand. And as I said, well, we have to running out of time a little bit. So I will just state the result, and then we will prove it next time. The result is that if we talk about, we can describe two types of primaries. Primaries with respect to this SL2R group only, which are sometimes called quasi-primaries, and primaries with respect to the whole group. Now, if we have a real primary operator, then at the level 1, it annihilates and it gives us the formula, which this formula. And what I will tell you the next time is very dramatic because while we found this formula by L1 chi 0, we will also apply L2 chi 0 condition, and that will determine us anomalous dimensions in terms of the central charge. And by the way, these two conditions are enough. That's the last comment. They are enough for the field to be a primary. My last question is why it is enough? That's a simple question. Why I don't have to check L3? Yeah, it always, L3 always can be expressed in terms of this L1 and L2. So it's a real full primary. Okay, let's stop here.